So in this video, I'm going to review where the generalized expression for the binomial expansion comes from. And first of all, what is a binomial? It's any expression that has two variables. So for example, x plus y is a binomial, or x minus 3y. So any expression that's a combination of any two variables. So I'll start with some basic binomial expansion. So if we have power 1, that's just equal to x plus y. One that you might be familiar with is the square, and that expansion looks like x squared plus 2xy plus y squared. And cubic, we have x cubed and then 3x squared y plus 3xy squared plus y cubed. So what we want to see is what is the pattern behind these expansions and how can we find the generalized expansion. Now, one thing you would notice as I'm writing these expansions is that the number of terms here is one more than the exponent here. So we have 2 terms here, 3 here, a total 4 here, and 5 here. And if we go next to the 5th power, I'm not expecting you to know this already in the expansions, but more driving at what's the logic for these coefficients and these products. This would be y4 plus y5. So that has 6 terms. And we'll also notice that in each of these expressions, the exponents here of x and y, if you add those, they always add up to that same exponent for the expansion. For example, here 3 and 2, that's 5. And that's true for each of these terms for the expansion. That's 5. 4 plus 1 is 5. Same thing here. So those are some of the common observations. What we want to know is how do we explain these coefficients here. For example, it's 1, 4, 6, 4, and then 1 here. Again, here it's 1, 5, 10, so on and so forth. So I'm going to start by looking at product of this term. So p plus q times r plus s. So we have four variables here. And we apply the distributive property. So this would be same as p plus q times r plus p plus q times s. And then if we do the expansion again by applying the distributive property, we get 4 terms. So we get 4 terms. And essentially one way you can think about it is that I can take each term here and pair with these two, and same thing. So we have 2 terms that I can choose from here and 2 from here. So there's a total of 2 times 2, 4 terms. What if we take product of 3 such pairs? In this case, that first piece is what I just obtained here. So we can do that expansion. And then I'm going to distribute it over t plus u. And you'll see that again, we're going to get 8 terms. And that's because we have 2 here, 2 here, 2 here. So we're really pairing each one. For example, we'll get terms like p, r, u, where we select p here, r here, u here. So we know that if you have several of these, we're just taking 2 to that power. So when we have 3, that's 2 cubed. What about if we have 4? So if we have p plus q times r plus s, t plus u times v plus w, that's going to have 16 terms. And examples would be q. Let's say I selected q here, r, t, and w. So you will get terms like these depending on which ones you specifically select. Now, what happens in the case of x plus y to the 4th? So I want to take that information that we did for the general case and apply it to the specific. That's what we're interested in, this expansion of x plus y to the power of 4th. So here, if I select x here, a y here, and x here, we're going to get this term, which is same as x cubed y. But now we can get this x cubed y also if we were to select a y here and X here, and X here. So it's really, if I had to list them all, it's just about arranging 3 X's and 1 Y, because that's really what I need ultimately in that product. And I can select them from these different pieces here. So here, in this case, it's simple enough. I can write them. It's basically putting the Y in different places. And then I put Y at the end here. So we know that we're going to have 4 such terms. And that's why when we do the expansion here, we'll have 4 of these, and that's why we get 4x cubed y. I'll go back to where I wrote the expansion for x plus y to the 4th. We do indeed have 4x cubed y. So that's sort of the basis. Now, how do we generalize from this? Well, this problem of arranging 3 x's and 1 y's is basically we have 3 identical letters and 1. In this case, the number of such arrangements would be 4 factorial, which is the total number, divided by the numbers of each kind. And this is same as for C1. So if we were to look at, for example, x squared, y squared, this is how many different ways I can end up with 2 x's and 2 y's. I mean, it could be xy, xy. So again, it's about arranging 4 of these letters where 2 are x's, 2 are y's, and that would be 4C2. And that 4C2, if you compute, that's 6. So x squared, y squared will have a coefficient of 6. So that's kind of where all these coefficients are coming from. So what I'm going to do is to list all of these out for this particular one, x plus y multiplied 4 times. That if we want to get 4 x's, this would be 4C0, because we're just arranging 4 x's. There's no y. So this is 1. Next we have 3 x's, 1 y, so that's 4C1. And then 2 x's and 2 y, that's 4C2. And then 1x, 3y, that's 4C3. And finally all y's. And you will see that we have 5 of these. Again, was 1 more than the number here, as we observed earlier. So we can generalize this for this particular case. X plus y to the 4th would be 4C0, x4, then C1, x cubed y, or you can write it as y to the 1, 4C2, x squared, y squared, 4C3, x, y cubed, and then 4C4, y fourth. And if we were to write these as numbers, we have this is 4, this is 6, this is 4, and that's 1 here. And I do want to comment here that 4C1 is equal to 4C3, because in general, I won't go over why that is, but in general, NCR is equal to N. I do that in a separate video. So here, if I were to write the numbers instead of these generalized combination expressions, we'll get what I started in the first slide. Now, our goal is to see how we can generalize this to higher powers. So, for example, if we wanted to go to x plus y to the 5th, we'll have terms like x cubed y squared that requires us to arrange 3 x's and 2 y's. And this is really about arranging 5 letters where 3 are identical and the other 2 are identical. So 2 y's, 3 x's. And this is same as 5C2. We can also use 5C3, but as a convention, we're going to choose 5C2, which reflects the number of y's. So we're kind of pairing this. We could either write it like this, go with the x's, but generally convention is to use that, but they're both equivalent. So now we can kind of extend this to the more general case, that is, if instead of 5, it's n. So we're going to multiply this binomial expansion. So n times. And here, we want to look at a particular case which has j y's and the remaining are x's. The total is n, so these two add up to n. So here we're arranging n minus jx's and j y's. The total is n factorial, so we divide it by n minus j factorial and j factorial, which is same as ncj. So this is the generalized coefficient of that, which means that x plus y to the n, so this is where I'm going to write the generalized binomial expansion, nc0xn, then the power of x goes down by 1, and we get y to the power of 1. Then nc2, x goes down, and minus 2, y squared. Then nc3, xn minus 3, y cubed. And then in the most general case, ncr, xn minus r, yr, and then the last term would be ncn y to the n. You'll notice that both of these are 1, but we want to retain this general coefficient, so I'm going to leave that in that form. That's typically what how it's left. So this is sort of the binomial expansion that comes in handy in a lot of the problems. But I wanted to go over what the basis of these coefficients is and how that's related to arranging x's and y's in these products, and why we get these specific numbers. They are, of course, part of the Pascal's triangle. I didn't allude to that, but basically that's what they are, and this is the generalized expression. So that completes this lesson.